Hello, everyone. Anybody out there? Good morning. Good morning. Da, 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 da. Good morning. Good morning to you. Good morning. Good morning. Da, 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 da. Hey, anybody out there? Yeah, no problem. Bonnie, thank you for the question. Uh, Remember, a lot of these concepts are meant to introduce you guys to these concepts, okay? So that way, when you get into grad school or life grad school, meaning when you start working and you're kind of learning things on the job, that these concepts at least have been familiar with. Oh yeah, I remember that, and then you can kind of develop them on so and so. So I'm gonna draw. I brought some paper and a pen, and I'm gonna draw you a couple examples here. Okay, so if I had, um, oh Lord, my drawing skills not very good, but let's say we had two bones, bone one and bone two. Okay. We have bone one and bone two. Arbitrary bones doesn't matter because I couldn't draw it if I had to, if I had to draw a specific bone. But does this make sense that any force that is parallel, now I'm drawing these arrows outside of the bone, but does it make sense that any bone that's parallel, any force that's parallel with those bones would be trying to press the bones together, like to add stability to the bones, right? Trying to pull one bone into the other to maintain and make sure those bones don't slip away. So remember when we were growing up, we used to do that game where you'd hold your hands together and you'd try to squeeze together and someone would come and knock them away. So your force is parallel to your hands, and the reason they were able to knock them away is their force was perpendicular to it, right? So the point is that muscles, when they pull, and obviously it depends on the range of motion, and again, that's graduate school stuff. But what I'm trying to show you is that when muscles pull on a bone, so I'm going to give you an example here of, let's say this is a humerus and an ulna, and that arrow represents how your bicep would be pulling, right? So that's a familiar concept, right? Doing curls, and at this angle, that would be roughly the direction of pull for the bicep. So what I'm trying to show you is that bicep pulling at that angle actually has two functions. One is a rotary function. Let's see if I could draw this nice and pretty. So the big arrow is what we call the resultant. In other words, that's the actual pull of the tendon. But then the components, the X and Y component, if you notice, the Y component that's perpendicular to the long bone, That's actually the component of this force that's actually trying to influence elbow motion. Pulling to try to rotate you, pulling to influence motion, causing motion with concentric, preventing motion with isometric, allowing motion with eccentric, slowing down motion with eccentric. And then this component of that bicep resultant is parallel to the long bone, meaning that if this is the forearm and the biceps brachii here, this is the rotary, and this is the stability, the stabilize, the pull that's trying to draw the lower arm into the upper arm. So again, here's the bicep, rotary component, stabilizing component. Because again, one thing that I didn't have emphasized to me in undergrad that I wish I did, that's how I kind of pick what information I think is of importance, is that when I got in the real world, I was a practicing athletic trainer for years and years and years. It's like, man, looking back, what are some things that I wish I knew that I could have had in undergrad so that in grad school I could have developed? And that's muscles, skeletal muscles aren't just there to move you. A lot of times they are there to stabilize you, to prevent hypermobility in ways that the bones are not supposed to move. And there's a lot of application here. That's one reason why women, young girls especially, have a higher risk of ACL tears than boys, is because their muscles aren't as stiff. They don't have natural tone stiffness. Now, your trade-off is you have more flexibility. But muscles serving as joint stabilizers when you land and you jump up and then you load on your lower leg, and those hamstrings, as an example, don't pull that lower leg in a stabilizing fashion, and you allow some translation of those bones about each other. So the intent is to just basics show you through vectors and through physics how a muscle can do both function as a rotary component and as a stabilizing component, because the muscles pull at angles, and some of that component is rotary and some of that component is stabilizing. Now, it just so happens that my arm is here, that the rotary component could be here and the stabilizing component could be there. Like if your knee was hanging off of a table, watch, I'll give you an example here, and your quad. Now, obviously, this is just an arrow that represents the angle that maybe the the patella tendon would be putting on your tibial tuberosity. But again, the concept is still there, that you have a component, and obviously I'm not drawing these to scale, I'm exaggerating them to show the effects, but you have a component of that pull that's perpendicular, thus rotary, and then you have a component of that pull that's translatory, that's parallel, and that's stabilizing. And then the muscle itself lives somewhere in the middle most of the time. Okay. So Bonnie, let me know if that was helpful. And again, to see intent, that I'm just trying to show you, not just tell you, but show you with arrows how muscles serve both movement and stabilizing components. And thank you for the question. Yay. No problem. And again, it's if you look in your, to me, the best example is in your support materials. You have I want to say it's a deltoid, but I don't trust my memory for that kind of stuff. But you have an example in your support materials that has a great illustration of a bone and a bone, and they have a resultant and they have a rotary stabilizing. So there's a lot better than what I can draw. Oh, my pen. But you have an example in your book that I think summarizes the concept that I'd like for you guys to understand. And yes, I know that my Raging Cajun shirt is red and my Mets hat is orange, but I'm a weirdo. So I embrace it. I wear it like a badge of weirdo armor. All right, let me know. Oh, what a great question. No, those are two totally separate things, okay? So momentum is mass in motion, and that is taking the mass of an object times its change in velocity. Moment is torque. It's a biomechanical term for torque. So you can use moment and torque interchangeably. And what it is rotational forces. So moment is 100% just dealing with kinetics, just dealing with forces. Momentum deals with mass and motion. So momentum is actually a kinematic term, a movement term. Moment is a force term, a influencer of motion term. Moment is left side of Newton's second law, and momentum can be shown to be on the right side. When I say shown to be on the right, you gotta play around with the equation. But the point is that they are two totally separate concepts. Something that can be interchanged with moment is torque. So you think about a mechanic using the word torque, like a torque wrench, a rotational wrench. And also think about if you're having a tough time changing like a lug nut on a tire that's flat, you want to get a longer, we used to call it a cheetah stick, but basically like a cheat pipe, where you get a long pipe, you put it in that wrench, and you can more easily influence the rotation of the lug nuts. That's torque. In mechanics, they use the word torque. Engineers use the word torque. Biomechanics, we use the word moment, but they mean the same thing: rotational influence, rotational forces, forces that are trying to cause something to spin. Not all forces try to cause something to spin. If I have this baseball and I supply a force right in the middle of the ball, that force is trying to make the ball translate, but there would be zero moment. There would be zero rotational force unless I supplied that force out to the side. Now, because I have force and moment arm or torque arm, I have a perpendicular distance that force application is applying away from the axis of rotation. Now I have a moment. Now I have a torque. So not all forces create moment, or not all forces cause moment. Imagine as a kid if you were on a merry-go-round and someone, instead of trying to pull the metal to spin the merry-go-round, tried to push into the center of the merry-go-round wouldn't do anything. So you're applying a force to the merry-go-round, but you are not supplying a torque. You're not supplying a moment. That force has to have an element of perpendicularity. That's why doorknobs, when you open and close doors, that's why they're far away from the hinge. They're far away from the axis, so that when you apply your force, it's far away from the axis. There's a big perpendicular distance that is the door itself, so that you can supply moment, you can supply torque. Let me know if that helped clarify those two concepts for you. And once again, thank you for your question. Awesome. Keep them coming. Keep them coming. Did Physics 207 hopefully help you guys with some of these concepts? Once we're able to get, I'd say maybe another year of grace period for those that are correct, then I can really start getting into some cool physics stuff. Yeah, absolutely. So remember that first class levers can serve all four functions of a simple machine. So balance, especially uh, uh, advantage force, torque, advantage speed and range of motion, and then change direction. I'm writing this down. Change direction of applied force. All right. So let's first start with first classes. So the first class lever in its simplest form is a teeter-totter. Right? Here's a teeter-totter, here's an axis, and the teeter-totter does this. However, the teeter-totter you may find in the park doesn't shift around, right? It stays fixed. So how you have to think of first-class levers in terms of like just their definition is a teeter-totter can change the direction of an applied force, meaning if I pull this part down, the other end goes up. An example of that is like a good morning exercise. I think I'm calling it that, right? Watch, let me show you. Exercise. So, let me try to do like a deadlift more. Exercise. Okay, that's not bad. So watch. So the concept is during the deadlift, the hamstrings. Now I'm just looking at it. Remember how I emphasize you got to look at these levers in the body muscles by muscles because some of them are doing different things. But if we look at this like from the hamstrings perspective, here's the pelvis. Hamstrings help to produce hip extension by pulling the pelvis like this, and thus the upper extremity comes up. Does that make sense? Change the direction of an applied force. Hamstrings pull down on the pelvis, and the other part goes up. Okay. Balance. I mentioned that a lot when in the lower extremity, like your subtalar joint and your ankle joint. You have, the teeter-totter example when you're trying to balance on one leg. That when you're weight bearing, you're balancing all the time when you're standing. But if you really want to see it, balance on your foot and don't hold on to anything. You know what you're going to notice? Your muscles are constantly tugging. Not like working, but they're constantly innervating because you're constantly swaying. We call that sway velocity in biomechanics. But that's first class leverage because muscles on this side are working with those in the front and the back, and they're all kind of helping to maintain your center of mass over your base of support. Okay. So the emphasis that I told you in the lecture is when you hear key words, think leverage, balance. Your mind should immediately go to first class leverage. Now, in the teeter totter, though we can't move the axis, we can move the forces. In other words, if I'm teeter tottering with my brother, my older brother, who is a lot heavier than me as a kid, and we wanted to balance the teeter totter, well, of course, we couldn't be in the same place on the teeter totter because he's heavier if he's on this side. So if we both get in the same place, it's going to do this. So what we have to do is we have to say, hey, Jason, my brother, come closer to the axis. So if my brother scoots up, me being far away, now I might be able to balance the teeter totter because my less force is being applied farther away, his greater force being applied closer to, and we can balance. So that's kind of how first classes kind of work with balance as well. Then you get into force and torque. And what I try to emphasize in the videos, go back and watch them, is that there's an inverse relationship to speed and torque. If I'm trying to make this pin rotate as fast as I can, I want to supply that force as close to the axis as I can. Because a short change in distance here is going to produce a large change in distance there. Let me try to go up on the board and draw something, and then I'll come back and try to explain it to you. Okay, check this out. You know how in circi, you might get a gymnast and they want to sling the gymnast high up in the air. Well, to make them go high up in the air, you got to make them go fast. To go high is to go fast if you're leaving the ground. So let's pretend the teeter totter that we're going to sling the gymnast up in the air starts where A is on the bottom and B is on the top. Now, obviously, if we have a gymnast on the end, we better have a large force on this end because, again, smaller moment arm. Okay, so naturally that's going to produce less torque. So we got to compensate by having large force. That's why the gymnasts that sling the other people usually jump from high up to create momentum and create large forces, or they'll have multiple gymnasts all jump together, large forces to compensate for the short moment arms. Here's my point. If that lever doesn't snap in half, if that lever doesn't break, then it's logical to infer that the change of B from the bottom to the top has to occur at the same exact amount of time as the change of the lever on the left from A to A. In other words, the right side has to go from bottom to top in the same amount of time, bottom to top to bottom, because remember, we're crisscrossing and I'm showing you a before and after. So B on the right has to go from top to bottom in the same amount of time as A has to go from bottom to top, unless it snaps. So if it doesn't snap, then what that tells me is that if B has to run a shorter distance in the same amount of time as A has to run a longer distance, who has to be running faster? In other words, if they get to their end destination in the same time, A has to be traveling faster to get there because it has to travel a greater arc distance. That's the secret to third class leverages or speed and range of motion. Third class always favor speed and range of motion because the force is always going to be, your muscle force is always going to be closer to the axis. So therefore, the distal end is always going to have to run faster. Think of it like this. If you were going to run with a partner around a track, okay, here's a track, an oval track. Forgive me, it looks like a potato. But if you were going to run with a partner around a track and your partner was on the outside lane and you were on the inside lane, and y'all both started at the same time and you both finished at the same time, your friend, your partner, had to run faster than you, because the only way to travel a greater distance in the same amount of time is to go faster. Okay. So, first class leverage in the body can favor all of these things, but they can't do it all at the same time, is what I'm trying to get to. Some muscles, like the bicep, insert close to the elbow axis. They're going to favor speed and range of motion. Other muscles insert far away, like the brachioradialis inserts way over here. It won't favor speed and range of motion. Did you see my last lecture where I kind of went into those kind of things? It moves far away. It would have to create a huge arc distance of travel. That's like if I was trying to flick the bottle, like if I check this out. Let's say I wanted to split the bottle. Look how fast, you couldn't even see it because it was so fast. Here's the force, there's the axis, there is a huge speed coming on the other side. But if I was going to apply my force not close to the axis but very far away, there's no way I can make the bottle move as fast as if I do that. That's the trade-off. Now, the so what is, if you're having to lift something super heavy, then naturally it won't go very fast. So I don't care if it goes fast. If I'm trying to push a car that ran out of gas, I know I'm not going to be able to make it go fast. So torque, large moment production, inherently doesn't favor speed, but it favors large torque and moment. Okay. So insertions far away from an axis favor torque at the expense of speed, and muscles that insert close to axes favor speed at the expense of torque. Let me know if that was helpful. All right. Yeah. All right, guys, 10 more minutes. Then I got a Zoom meeting. Everybody say Zoom, Zoom, Zoom. That Zoom, Zoom, Zoom. Watch the lectures, watch the lectures, watch the lectures, watch the lectures. Like I said before, guys, one of the positives, I know it's 220 and crazy things happen, and the hurricanes came, and we didn't have Wi-Fi here at Bourgeois for a couple weeks. But one of the positives about using my spring lectures for this part of class was that the grades were incredible. So I guess my point is that it worked in the spring for students to regurgitate the key points that I asked them to do it. So there's no reason why you guys can't do the same thing. Just trying to be positive. All right, last call for questions, guys. This is kind of awkward just sitting here. All right, guys. I hope that was helpful. Always hit me up if you need any clarifications, even if it's FaceTime or something. If you need help, don't wait till the night before the test, please. But if you need some help in the next week or half, let me know. Okay. All right. Later.